All right, welcome to today's webinar. Today we're going to be covering protein. We're going to be talking about the structure, the function, and the ergogenic potential of protein. You may remember, you will remember from your Certificate 3 and Certificate 4, we did a little bit about the macronutrients. We talked about fat, we talked about carbohydrates, and we talked about protein, but we didn't really go into a lot of detail about either the structure or the function or even the ergogenic potential. So that's why we're going to elaborate on that in this ad hoc webinar. So let's begin. So protein, apart from water, which is the most abundant substance in the human body, protein is actually the second most abundant, obviously dependent on whether the person is, a fit and healthy person or whether they're overweight, because an overweight person would very much likely have more fat. But typically, an average healthy person has about 50% of their dry weight being comprised of protein. So all cells are comprised of protein, so they have structural elements and they have functional elements to these proteins. So some of the structural elements are the connective tissue that really holds the whole of the cell together. So the cell membrane is comprised of protein. And also some of the structures inside, like the sarcoplasmic reticulum or the endoplasmic reticulum that contains calcium and things like that, that is also comprised of protein. So it's structural elements. The functional aspects of protein would be things like the building molecules of DNA, obviously within the nucleus, within the cells. And also think about the mitochondria, which are these energy factories. They are primarily made of protein as well. And think about the sliding filament mechanism in muscle contractions. If you think about those myofilaments, actin and myosin, they slide across each other and they're often called protein strands because that's exactly what they're made of. So protein is essential, as I said, it's part of every cell within the human body. Protein can also be used as an energy source when carbohydrates are depleted and fats not readily accessible. Now you remember from your Certificate 3 and Certificate 4 that the primary energy sources for aerobic metabolism are carbohydrates and fats, and the primary energy sources for anaerobic metabolism are carbohydrates and phosphocreatine. In situations where you're doing relatively high intensity, long duration exercise, where your carbohydrate sources are your primary energy source, both aerobically and anaerobically, but primarily aerobically, if you're doing that high intensity or relatively high intensity, you don't have accessibility to fat because you need so much oxygen to break down fat as an energy source, so it cannot really be a driver for energy creation. So what will happen is your carbohydrate levels start to drop down and you start using protein, and the most readily or the most labile source of protein is actually muscle tissue within our body. So muscle tissue will get broken down during the high intensity, long duration, sort of the ultra endurance type activities. Muscle tissue will get broken down, the amino acids will get released, and some of those amino acids will go to the liver and get converted into glucose, and these are called gluconeogenic amino acids. So we have ketogenic and we have gluconeogenic amino acids. So gluconeogenic simply means ability to create glucose from a non-carbohydrate source, in other words, an amino acid. So at rest and during normal day-to-day activities, we really don't use a lot of protein as an energy source. Only about 3 to 5% of our energy comes from protein because it's, again, used for building structures. It's not used as an energy source. But during these ultra-endurance activities, that can go up to about 10 to 15%. So it can be a potential source of energy during times when carbohydrate levels are actually starting to drop down. So let's look at some of the other functions of protein. We've already talked about the structure. We talked about the energy provisions that can come from protein. What about transport? When we're talking about transport, what we're really talking about is transport within the blood. So hemoglobin is primarily made of protein, and obviously hemoglobin attracts oxygen and allows oxygen to be transported around to all the cells that require it. So that's another really important function of protein. Protein is also the building blocks of hormones, and certain amino acids are actually neurotransmitters, and sometimes the isoforms of, or the variations of amino acids are actually neurotransmitters. Glutamate would be an example of that, and there's another one called GABA, or gamma aminobutyric acid, which is a very important neurotransmitter. So some of them are excitatory and some of them are inhibitory neurotransmitters, but they're all made of protein and they're all absolutely essential to function. Chemical reactions, enzymes facilitate chemical reactions, and enzymes are primarily made of proteins as well. So again, another really important function of protein. Immunity, all the white blood cells, just like the red blood cells, are made primarily, their cell membranes certainly, are made of protein, and a lot of the structures within them, the lysosomes, etc., are actually made of protein. And it's interesting, one of the amino acids called glutamine has been studied to be really, really important for supporting the immune system. So and glutamine is actually the most abundant amino acid we have in our muscle tissue. About 60% of our muscle tissue is actually made of glutamine. So the acid-base balance is largely regulated by hemoglobin. And again, we talked about hemoglobin previously. So that can actually regulate whether the blood actually becomes more acid or more alkaline. So, and again, obviously hemoglobin primarily made of protein. Fluid balance, a lot of the hormones that regulate fluid balance, like aldosterone and antidiuretic hormone, regulate the flow of liquid in and out of cells. So fluid balance is really controlled largely by protein and the hormones that are actually made from those protein. Movements, I mentioned earlier, the sliding filament theory. Again, that contraction of muscles is facilitated by movement of protein strands across each other. So again, essential for living. Growth and repair, and this is what a lot of bodybuilders and athletes are really concerned about in terms of protein and just how much they should consume, because protein is the building blocks of muscle tissue as well as all other cells. Throughout the day, cells are constantly being broken down and repaired. In fact, there is a process called apoptosis, which means natural cell death. It's a way of preventing mutations from occurring in cells. And we lose somewhere between 20 and 30 million cells within a day, and they all need to be replaced. So again, this growth and repair is largely regulated by the amount of protein that we have. So a typical person in an average day will break down about 200 to 300 grams worth of protein. Now, about 75% of the amino acids within that protein can be resynthesized back into protein structures, but we lose about 25% of that protein, and therefore that obviously has to come in the diet. So 200 to 300 grams, 25% of that is about 50 grams to 75 grams of protein that an average person will actually need in the day. And that's not somebody who's doing an enormous amount of exercise, just as an average sedentary person. But we'll talk much more about that later. Right, so protein compared to carbohydrates and fats, there's one major elemental difference between carbohydrates and fats, which are only comprised of carbon, hydrogen, and oxygen. Protein, the one extra thing that all proteins have, is nitrogen. Some of them also have sulfur and selenium as little trace elements, but the important thing with protein is that it contains carbon, hydrogen, oxygen, and nitrogen. So all of these elements are bound together in different numbers to form amino acids. And the amino acids, as we know, are the building blocks of proteins. So, amino acid general structure. If we look at what's called an alpha amino acid, if you look at the center of that structure on the right hand side, there is right in the middle, there's called a central carbon atom, or it's called an alpha carbon. Coming off that, there are functional groups. So you can see there's a hydrogen atom coming off one side. There's an amino group, and an amino group by definition is one nitrogen plus two hydrogen atoms. Then on the other side, there's a carboxylic acid group, and you can see what the structure of that is. It's one carbon plus two oxygens plus one hydrogen atom. Then And this is what really determines what type of amino acid it is. There's a variable side chain, which is very specific to each individual amino acid. So the side chain could be a straight side chain, it could be a branch side chain. Now, if you think about what that term means, branch chain amino acids, and again, we'll talk about those a little bit later. So this is all the structure of the chain that's actually coming off the side there. So you can also have ring type ones, which are called aromatic. So different structures can really determine the type of amino acid that we're referring to. So, classification of amino acids. There are more than 500 amino acids in nature. The human body doesn't need that many, but we can actually classify them in many different ways. We can classify them according to their function. So some of them could be, structural. Some of them could be energetic. We could define them in terms of their structure. So we were just talking about the alpha. In fact, if I can quickly just go back to this previous slide, if you look at that central carbon atom, that is called an alpha amino acid. If you have a side chain which is attached to the carbon that's in the carboxylic group, that's actually called a beta amino acid. Now, majority of amino acids in the human body are actually of the alpha form. So generally amino acids that we talk about are all the alpha type of amino acid. So the structure, we were talking about the chains that actually come off. They could be a straight chain, they could be a branch chain, they could be a ring-shaped formation coming off the side. The polarity, some of them actually have a positive charge, some of them have a negative charge. That's another way of classifying amino acids. Some of them have different levels of acidity versus alkalinity, so the pH is another way of classifying them. Also the type of side chain, we've just mentioned that, so that's another way of determining what they are, or the classification. The metabolic pathways, I mentioned earlier the ketogenic and the gluconeogenic. So some amino acids get converted into ketone bodies. Some of them get converted into glucose, so they can be categorized as either or, and some of them can be ketogenic as well as gluconeogenic. So in some classifications, you look at those as looking at the solely ketogenic, the solely gluconeogenic, and then the ones that can actually do both functions, dependent on what the state of the body is at the time. So, and another way of classifying it is the way that they, or whether they can actually be synthesized in the body. And you'll have heard of these terms, essential and non-essential amino acids. And this is how we typically classify most amino acids. Certainly in the fitness industry we do. So there are 21 proteinogenic or protein building amino acids. So that's part of their function. So what these amino acids do then, of course, is synthesize protein tissues. Of those 21 protein building amino acids, 9 of them are essential. They're often called indispensable amino acids. They can't be synthesized in the body, and therefore they have to be provided through the diet. So there are 4 non-essential or dispensable ones, which means that they can be readily synthesized. Really in all conditions they can be synthesized. And then there are 8 conditionally essential amino acids, which used to be categorized as being non-essential, but under certain conditions they cannot be synthesized. For example, with premature babies, they have an inability to synthesize some of these amino acids. People who are suffering trauma, such as burns victims, and people undergoing traumatic stress, lose the ability to synthesize some of these amino acids. So they're referred to as conditionally essential amino acids. So again, this is one of the ways of classifying the essential, the conditional, and the non-essential. So if you look at this table, you've got the list of the 9 essential, the 8 conditional, and the 4 non-essential. I'm not going to go into a lot of detail on those, except to say that we have starred the branch chain amino acids. And what you'll notice is that they are isoleucine, leucine, and valine. And again, we'll talk about those quite a lot more as we go through this presentation. So when individual amino acids get digested and then they get recombined together within the human body, you're taking two separate amino acids, and what you're doing is you're creating what's called a peptide bond between those two amino acids. And by definition, a peptide bond is a combination or a combining of the carboxyl group of one amino acid with the amino group of the other amino acid. So when they combine together, if you look at that orange sort of shaded area, you'll notice what's in there is two hydrogen atoms and one oxygen atom. So when they combine together, they actually create water, so H2O, which gets released. And you can see that when the peptide bond gets created, water gets released. So what you're left with is a dipeptide, which is two amino acids, and then water. And that process is actually called condensation. And if you think about what condensation means in day-to-day terms, it just means the creation of water. Condensation on the windows means that water is being created. And that's exactly what happens in this process. So when you're combining amino acids together, you're actually creating water. When you're breaking down amino acids, for example, when you consume whole proteins and you need to digest them enzymatically and break them down, you actually need to add water. So this is why you might have quite often heard that if you're on a high protein diet, you need to drink lots of water, because water is essential for this enzymatic breaking down of the protein into the individual amino acids. So if we put a bunch of these amino acids together, or if we put three of them together, we create a tripeptide, and if we create a bunch of them together, we create what's called a polypeptide. So on the right-hand side of the slide, if you look at what we have there, we have a bunch of different amino acids creating a peptide chain, and then they tend to create either sort of a helical or a spiral structure, or sometimes they create flat sheets, and that really determines what type of protein they will actually create. So, for example, you probably heard that DNA is a double helix. So again, the protein structures are both in helixes, and they kind of bind together. So, put a bunch of these polypeptide chains together, and you'll actually create a protein. So if you look at the far right-hand side, you're assembling a bunch of subunits, which are these polypeptide chains. And if you pack them all together, you create what's called a quaternary structure, which effectively is a protein. And that's actually an example of a globular type of protein. All right, so nitrogen balance and protein metabolism. You might have heard the term nitrogen balance, and you remember the one thing that differentiates protein from carbohydrates and fats is that it does contain nitrogen. So the most readily available source of nitrogen in our diet comes from protein. We do get trace elements of nitrogen from other non-protein sources, but almost all of the nitrogen really comes from protein. So the nitrogen content of protein foods consumed can be compared with the nitrogen excreted through feces, through the urine, through sweat, through sort of attachment to your hair and things like that. And what we can do is look then at the nitrogen balance. So what you're doing is comparing how much nitrogen you've actually consumed with how much nitrogen you've lost. So if you have a positive nitrogen balance, what that means is that you're actually accumulating nitrogen within the body. In other words, your nitrogen intake is greater than your nitrogen loss. So you've created nitrogen structures, in other words, protein. So that is an indication that you're actually in an anabolic state, which is what most athletes actually want to achieve, because you want the muscles to obviously increase in size. And negative nitrogen balance, obviously, on the other hand, means that tissues are being broken down faster than they can be resynthesized, and that implies a catabolic state. So, factors affecting nitrogen balance. The one thing that we know is that hormones have a major effect on nitrogen balance. So men have larger muscles generally because they have high levels of testosterone, and testosterone, of course, is an anabolic hormone. It takes amino acids and resynthesizes and replenishes protein structures or muscle structures that have been broken down throughout the day. And it's not just muscles, of course, it's connective tissue. It's tendons, it's ligaments, it's collagen. It's all of these structures that constantly get broken down and need to be replenished. So testosterone is one of the hormonal factors. Growth hormone is another one. That's a very anabolic hormone. Insulin, interesting enough, is a very anabolic hormone. We think about insulin generally as taking sugars or glucose into the cell, but as it opens up the cell to take glucose in, it also facilitates the transport of amino acids into the cell. So you've got the building blocks right there, and if testosterone is in there as well, then you can start resynthesizing muscle or connective tissue. IGF, or insulin-like growth factor, is a hormone-like substance as well, which again facilitates the regrowth or the recovery post-exercise. So exercise in and of itself obviously causes muscle tissue to get broken down. So if you do have a particularly poor diet and you're doing high intensity exercise, it is quite likely that you will fall into negative nitrogen balance. So the way to prevent that, of course, is by making sure that you have sufficient protein intake. So again, it's that balance with how much exercise you're doing and how much protein you're actually taking in. So it's not just the quantity of protein though, it's also the quality of the protein and potentially even the timing of protein. Timing of protein has been talked about for many years, and that we'll talk about that a little bit later. All right, so let's first talk about the quantity of protein. There was a study done by a fellow called, I think his name was Pete Lemon, in 1995, and it was entitled, "Do Athletes Need More Dietary Protein and Amino Acids?" And the conclusion from this study and from lots of follow-up studies was that for a sedentary individual, the recommended daily allowance is 0.8 grams per kilogram body mass per day. And that is still recognized as being the requirement. So if you're 70 kilograms, multiply that by 0.8, you'd need about 56 grams of protein per day if you were sedentary and not doing any physical activity. So this particular study was done on endurance athletes and strength athletes. And these were not recreational people who were training 45 minutes a day. These were people who were training between 90 minutes and 3 hours a day. So they were really serious athletes. And what they found was that with endurance athletes, of course, they had a higher breakdown of muscle tissue, and especially for the ultra endurance athletes, some of that protein was used as an auxiliary fuel. And therefore the recommendation for endurance athletes was more than the sedentary, so up to about 1.2 to 1.4 grams per kilogram body mass per day. So for strength athletes, this particular study and a number of studies that were done as follow-up from this highlighted that yes, they do need more than endurance athletes, but not substantially more. Strength athletes, and again, these are people who are training up to 3 hours a day, required about 1.4 to 1.8 grams per kilogram of body mass. And this was primarily for maintaining muscular mass, but also giving sufficient protein to actually optimize muscle mass. So it's really for muscular development. Now, a lot of bodybuilders, especially the non-natural bodybuilders, so that those who are taking steroids, will be taking upwards of 2, 3, 4, and even 5 grams per kilogram. Now, obviously, they can't get that from whole food sources because they'd be consuming about 5 kilograms worth of steak if they had to do that every day. So they're getting that from supplements. Now, the question really comes in as to why they need to take that amount when these strength athletes in this study and lots of follow-up studies only needed 1.8 to get them into positive nitrogen balance. Well, we need to consider steroid use and abuse. Taking high dosages of steroids allows you to recover much more quickly, and therefore it allows you to do high intensity exercise and recover almost within 24 hours. And this is why it's been suggested that people who are taking anabolic steroids and growth hormone and all of those other type of anabolic facilitators might need higher dosages, but anyone who's natural would only need 1.4 to 1.8 grams per kilogram of body mass. So aside from quantity, it's really important to look at the quality of the protein that we're consuming. Now, over the last 30 years, there have been many different ways of classifying the quality of the protein. So we have things like net protein utilization, the protein efficiency ratio, NV, which I think stood for nutritional value. But the one that's that's used primarily nowadays is what's called PDCAAS, or the Protein Digestibility Corrected Amino Acid Score. And this is based on the profile of the essential amino acids within the protein that you're consuming, as well as the digestibility of the protein. And therefore, what we're looking at is the ability of the protein to supply all the essential amino acids. So the highest possible score on the PDCAAS is actually 1, although it's interesting because it's normalized to a 1. There are certain proteins, for example, whey actually scores about 1.2, but it's normalized back down to a 1. So again, there are certain questions that we have to have on the PDCAAS. So if the highest score possible is 1, whey and casein both score 1 because it means that they are readily digestible and they contain the right quantities of all the essential amino acids that the body needs. Egg white, similarly, is 1. Beef, interesting enough, even though beef is effectively muscle tissue, and that's what we're trying to resynthesize, so it does contain all of the amino acids that are necessary in, obviously in cow as it is in human, but it doesn't digest as completely and as readily. So the accessibility of those amino acids is not as great as it would be with egg whites and whey and casein. Vegetarian sources are generally considered not to be so high on the PDCAAS because they lack, or they're very low in certain levels of the essential amino acids. So the legumes, for example, kidney beans, only scores 0.68 because it's actually low in the essential amino acid methionine, whereas whole wheat and a lot of grains only score about 0.4 because they're very low in the essential amino acid lysine. So it's often recommended that we combine the legumes and the grains together. Not necessarily. They used to say it had to be within a meal, but as long as it is within a few hours of each other, then you're getting all of the essential amino acids to effectively create a score of 1 when you combine them together. Because again, we don't think about just consuming one source of protein. We often combine different sources of protein. So let's talk about whey protein. Again, it scores incredibly high on the PDCAAS. So, but what is whey protein? Well, whey is effectively the liquid byproduct of cheese production. So the cheese itself is actually casein, and the liquid that's left on the top is actually the whey. So whey protein is a mixture of protein subfractions, and some of these subfractions are things like beta-lactoglobulin, alpha-lactalbumin, bovines, serum albumin, immunoglobulins, which are they're the antibodies that we have, which, interesting enough, in breast milk, from a very young age, from the first few days around birth, so a couple of days before and a few days after birth, breast milk contains something called colostrum, which is very, very high in immunoglobulins. And a neonate or a newborn child, their digestive system is very different from an older child or an adult in terms of its ability to absorb whole proteins. So a neonate or a newborn child, for the first few days or even weeks of life, can actually absorb whole proteins like immunoglobulins and like lactoferrin, which again is another immuno-enhancing substance. So they can be absorbed, and therefore they can supplement the immune system of a newborn child as it comes into the environment that it's presented with. But after a few days or months, the digestibility, the absorbability of those proteins reduces, and they need to be broken down into their constituent amino acids, or at least into a tripeptide. So, cow's milk, if we look at the content of whey and casein, cow's milk has got about 20% whey and about 80% casein. Human milk, on the other hand, has got about 60% whey and 40% casein. So human milk is actually a lot more liquid by nature. So you might have heard, if you're familiar with whey protein, you probably heard of the way that it's manufactured. So we talk about a concentrated whey protein, or an isolate, or a hydrolysate, or a hydrolyzed whey protein. Those are the main types. The original type of protein, if you're taking pure whey protein, what they do, remember, it's whey, which contains whey protein, but it contains other things as well. There's a lot of liquid, there's a lot of water in whey, there's also fats, there's also lactose, and there's a lot of bioactive products which really are essential to health. So when you're creating a concentrate, what they do, of course, is remove the liquid, Obviously, if you're creating a powder, you remove the liquid, and they remove a little bit of the fat as well. So typically, concentrates from 20 or 30 years ago used to have about 30% protein, whereas nowadays they're up to 90% protein because they've removed a large amount of fat and a certain amount of the lactose as well. Now, an isolate is a different way of processing it, and what they do is obviously the liquid goes, they remove all the fat, and almost all of the lactose as well. So typically an isolate contains about 90 to 96% protein. The problem that some studies have found with isolate is that the processing to create the isolate actually breaks down some of these bioavailable substances which are essential to health. So for a long time, isolate was considered better than concentrate because it was higher in actual protein. But if you're losing some of these bioavailable substances, then you need to maybe reconsider, maybe a combination of concentrate versus isolate. Hydrolyzed protein or hydrolyzed whey protein. Do you remember when we were talking about the condensation, when you're combining two acids together, amino acids together, and you release water, and when you split them apart, you actually need water? That process is called hydrolysis. So again, when we're breaking down breaking down a protein into its constituent amino acids, water needs to be added with the enzymes. And that's this process of hydrolysation or hydrolyzing. So what we're doing is taking a whole protein and partially digesting it, and therefore making the amino acids more readily available. But again, part of the problem with this is if you're breaking down the individual amino acids, some of those amino acids contain sulfur, and that sulfur really smells. It has a really horrible eggy smell. So pure hydrolyzed whey protein really doesn't smell very nice, and it's also a very expensive process. So again, it could be too expensive to be used in a typical protein powder. So again, maybe a combination of concentrate, isolate, and hydrolysate would actually be the ideal combination. So the great benefit of whey protein is it has really high concentrations of branched chain amino acids. Let's talk about what these branched chain amino acids are. Okay, so BCAAs, as most people refer to them as being, they're leucine, isoleucine, and valine. I mentioned that earlier. They're actually the only amino acids that are not metabolized in the liver. So they bypass the liver and they go straight into the muscle, and they get metabolized, incorporated straight into muscle tissue. Leucine, one of those branched chain amino acids, is considered to be the most important of all these branched chain amino acids because it actually is the only amino acid that stimulates muscle protein synthesis and is therefore the most potent anabolic branched chain amino acids. So previously, again 20, 30 years ago, branched chain amino acid supplements used to have a 1:1:1 ratio. So about 30% leucine, 33% leucine, 33% isoleucine, and the same amount of valine. Then they moved more towards having a higher concentration of leucine, so they moved to more like a 2:1:1 ratio. And now recently they've actually moved into an even higher with a 4:1:1 ratio. And again, that's largely because leucine is really seen as having this really potent anabolic quality out of all of the amino acids. Now, some of you will have heard of HMB, and it's always referred to as HMB. If you see it as a supplement, it just states HMB in big letters. HMB actually stands for beta-hydroxy beta-methylbutyrate. That's why it's always called HMB. It's actually a metabolite of leucine, so it's leucine partly broken down. And the original studies that were done on HMB actually looked at supplementing racehorses because they thought that there might be a potential anti-proteolytic or anti-catabolic effect. And with racehorses, who obviously have really high metabolism, they're doing real high intensity exercise, there was actually found to be a very protein sparing benefit of taking HMB. When they repeated the same studies, they weren't very well controlled studies, and these were done in the 1990s. On humans, they found that they didn't have the same potent anti-catabolic or anti-proteolytic effects that it did with horses. But it's interesting, in recent times, again over the last 10 years, recent studies on really well-controlled studies have found that taking somewhere between about 3 to 6 grams of this HMB per day had really quite powerful anti-proteolytic effects. And again, if you can minimize the amount of muscle tissue that gets broken down post-exercise, then effectively you can maximize the resynthesis. So again, it's all to do with the balance between catabolism and anabolism. So again, HMB is considered nowadays to be actually quite a beneficial supplement. It's fairly expensive, but again, a lot of bodybuilders and serious strength athletes are taking HMB now. So, finally, we need to talk about the timing of protein intake. So we talked about quantity, we talked about quality. Is timing important? Well, it's been largely accepted that post-exercise protein supplementation is beneficial. We've been doing this for years. Have a protein shake immediately after you've done a heavy training session because it optimizes recovery and promotes an anabolism. And there's a lot of studies that have actually indicated that that is the case. Research findings over the last decade or so suggest that a pre-workout protein supplement would be equally beneficial in terms of promoting anabolism, or sometimes, in some cases, even more beneficial. There was a couple of studies specifically that actually indicated that it was more beneficial than taking it post-exercise. Further research actually highlights that supplementation, as in the form of a protein powder, is actually not necessary at all, but that a protein-rich meal that's consumed somewhere within a 3-hour window prior to the workout is all that's required. Because basically what you're doing then is you're consuming whole proteins which take time to get digested. In fact, steak takes about 4 hours to actually empty from the stomach. So again, if you're having a whole protein, it takes time to get digested. The amino acids become readily available for the muscles immediately once they finished exercise. And that's really all you're looking at. So again, do you need to spend a lot of money on supplementation? Possibly not, because again, studies have indicated, again, with a protein-rich meal, 3-hour window, that's going to be ideal. So, the International Society for Sports Nutrition have a position on protein and exercise, and this was actually a position statement that was released in 2007, and there's a few points that they highlight here. First point is that exercising individuals need more protein than sedentary individuals, somewhere between about 1.4 to 2 grams per kilogram body mass per day. So we've already established that one. The specific amount is dependent on the amount and the intensity of exercise, the quality of the protein, and the energy and the carbohydrate status of the individual. So again, somebody who's low in energy and low in carbohydrates might need more protein because again, those gluconeogenic amino acids can actually contribute to energy creation. So concerns of protein intake within this range, the 1.4 to 2 grams, is potentially unhealthy are actually unfounded in healthy exercising individuals. The studies that were done on the negative side effects on the liver and the kidneys were actually done on people who had kidney insufficiency. So people who actually had problems with their kidneys anyway, and therefore the high dosages. Let me just explain why high quantities of protein can be detrimental. If protein is not incorporated into the body, the excess protein actually gets converted, part of it gets converted to ammonia, or ammonia gets stripped off it, and this actually happens within the liver. Ammonia is a very toxic chemical, so ammonia in the liver and partly in the kidneys gets converted to urea, which is a lot less toxic, and therefore it can be excreted. So again, having huge quantities of ammonia in the body potentially can be very detrimental. But again, with healthy individuals with good livers and healthy kidneys, they have the ability to do the conversion to urea and excrete it without any problems. Maybe taking 5 grams per day would be a concern. A few points on the ISSN position. Ideally, protein requirements should be met with whole foods, but again, supplement proteins such as whey and casein are safe and convenient options, and also relatively cheap options as well. Eating protein before, during, and after a workout can lead to improved recovery and gains in lean body mass. That's been well established over the years. Branched-chain amino acids have been shown to increase the rate of protein synthesis, decrease the rate of protein degradation, foundation and possibly aid in the recovery from exercise. So that's their position statement. And again, over the next few years, obviously there's going to be a lot more research that gets placed into this. Maybe more amino acids are going to be highlighted as being beneficial. Leucine seems to be one which is particularly beneficial for strength athletes. But again, there's a lot of research that still needs to be done. All right, that's a conclusion of my presentation.